Dear participants, welcome back to the day 3 of 5-day webinar organized by Department of Mathematics, Ramaiah Institute of Technology, Bangalore. Dr. Arulalan Rajan will continue. The topic for this session is Discrete Transforms, Computational Perspective. It's over to you, sir.
Thank you, Pasha. Thank you. I hope everybody had lunch. All are up for another 1.5 hours. Let's start. So I'll close my video and I'll share my screen. So let's start. We're going to look at discrete transforms, and I'm going to focus two of this transforms in this. Number one, I'm going to talk about Z transform, which we normally do for discrete sequences. And I'm going to talk about discrete Fourier transform. Discrete Fourier transform. I won't go into the details of this properties of discrete transform, Z transform, discrete Fourier transform and all. I will not do these properties, but I'll give a different perspective to this. So because the title of this is from computational perspective. So we're going to look at computational perspective of discrete, Z transforms, a discrete transform as such, from computational perspective. Is that okay? Okay, now let's start. Now, before we go on to Z transform, discrete Fourier transform, and all those stuff, let's look at what is a transform in the first place. It's a question. What is a transform? Some interesting concept. What is a transform? Why do we need a transform? That's the second question. We'll call this as question 1. Question 2. Why do we need a transform? Okay, so we will look at these two. Is that okay? Okay, so first the question. Transform. Okay. See, transform is basically something which changes mathematically we'll say, or probably it's something which is going to help us, or which helps us view a particular thing from a different perspective. From another perspective, but why would we want to do that? So that the analysis is easier. So we have answered both the first question and the second question. It says transform is basically something which helps us view a particular thing from another perspective so that the analysis is easier. So it's basically a tool. It's a tool, a mathematical tool, let us say, a mathematical tool that helps. It's a map that is used for analysis. Can we look at some example of very simple transforms? Let's look at very simple transforms. I would say not even very simple transform. What is the, the very idea of transform? What is the very earliest transform that we have studied? That's what we're going to look at. Very simple transform slash earliest transform we have ever studied. Okay. For example, let's look at the following. Suppose we want to multiply two, let's say, 7-digit numbers. We want to do two 7-digit numbers. So what is it that we are going to do here? So let x and y be two 7-digit numbers. Let x and y be two 7-digit numbers. So I call the product as P. Let P be equal to x into y. Is that okay? Let P be equal to x into y. Now, what is the easiest way of computing this? What is the easiest way of computing this? The easiest way of computing this is take log x base 10, take log y base 10. Then what do? We have log p base 10 is equal to log x base 10 plus log y base 10. So what has actually happened? First thing, what has happened is this multiplication has become addition of two logarithms. Addition of two numbers. Then what we do? We have log p base 10 is equal to, say, some z. So I want to find out p, which is the actual product. So what do? I basically do anti-log z. Is that okay? So I do anti-log z in this case. Now, what do we mean by this? So what we have done, I have had x comma y, which are 7-digit numbers. What have I done? Okay, let me redraw this. So I have two 7-digit numbers, x and another 7-digit number, say y. So I need to find what is the product of these two. This is product. So what did I do instead of that? Instead of getting directly the product, instead what I did, I basically took log x base 10. I took log y base 10. Then what did I do? I basically added these two fellows. I got log p base 10. And then what did I do? I basically did anti-log, and I got the final value product, which is p. Is that clear? So what have we done? We have done the forward process by taking log in this case, and then we did the reverse process, which is the anti-log. So we basically converted the 7-digit number to another number so that the computation became easy for us. So that the computation actually became easy for us. Yeah. So what we see is logarithm is basically a transform. Is that right? So what we did, we took logarithm and then we took the anti-log, that is the inverse of whatever we have done in log, and then we ended up getting the original product. So this is one thing, which means this logarithm helped us convert multiplication to addition. Let us look at another case. Let's look at example 2. What is this example? Now I'm going to look at exponential functions. I'm going to look at, let us say, exponential. What do we mean by exponential? Let us look at either e power x or a power x. You want to look at anything, let's do that. So what is this exponential function going to do? The function, you're going to, the moment you start feeding your x values, the function is going to, let us say, increase or decrease or whatever. And the rate of increase depends on how you're going to increment your x or whatever. Is that right? So we want to study this function. Is that clear? We want to study this function. So we want to study this function and analyze this. We want to study and analyze this function. Is that clear? So what do we do with this? Study analysis means, see, this all we are, I mean, the only thing that we are probably comfortable with is looking at straight lines. So let's write that. So the most simplest function growth that we that we can easily handle linear. If it is constant, you don't have to do anything. Otherwise, what to do? We basically look at linear. Otherwise, what you're going to do? We are going to look at linear, which is of the form y equal to mx or y is equal to mx plus c. So if I have an exponential function, the moment I take logarithm, so for exponential function, the moment we take
Sir?
Yeah?
Sorry to interrupt you. Is it, can you maximize this? Can you zoom it? Is it possible?
No, I don't think. Well,
Okay.
I'll probably increase the font size. Actually, I was using the same thing in the morning.
Okay.
Okay.
If possible, try to increase the font size, sir.
Yeah, sure. I'll do that. Okay. For exponential, the moment we take logarithms, natural log or whatever, what do we get? We end up getting what do we get? If we have e power x, we end up getting x ln e, which is 1. If you take a natural logarithm, you end up getting this. Therefore, what we see is we basically move on from exponential to a linear growth. Handling linear growth is easy for us. Is that clear? Therefore, so if we take natural logarithm, we end up getting x ln e, which is basically x itself. So that is going to be easy to handle. Therefore, this logarithm basically helps you in logarithm helps us in a computationally efficient, we'll say in computation, and looking at functions like exponential from a different perspective. Is that clear? So the question is, are there other transforms? This is at a very elementary level. The question is now, so question, are there other transforms used in engineering applications? There are lots of them. The most commonly studied transforms in engineering domain, at least in electrical branches, electrical sciences, the most commonly studied transforms are, we have yes, the answer is yes to this. So we have Laplace transform, B, we have Z transform, and C, we have Fourier transform and its variants. So what we see is this Laplace transform is typically used for all kind of continuous functions. So for continuous functions, we use Laplace transform. We use Laplace transform. Then for discrete sequences, we use Z transform. And for both discrete and continuous, we have Fourier transform. Then we have Fourier transforms. For continuous, functions, we have the continuous Fourier transform. For discrete sequences, we have discrete Fourier transform. We have two things. We have what is called as discrete time Fourier transform, and then we have a discrete Fourier transform. Is this clear? So we have, for different types of functions, we have different transforms to exist. Now, what is the need for these transforms? See, in the first place, we looked at logarithm to be useful for computational ease, and it is used for converting an exponential function to a linear function, or a power x, to a function which is non-exponential, and then try to analyze that. Now, what are the advantages of using these transforms? What is the purpose of using Laplace transform? We said for Laplace transform, we basically require the function to be continuous. So let's quickly look at this Laplace transform, Z transform, etc. So Laplace transform. So we have certain conditions for your f of t. Will not worry about anything. We will say it basically converts. Let us say a continuous variable t to a complex variable s. Where if f of t is a continuous function, of course, as I said, you have requirements for Laplace transform and all. So we'll say if f of t is a continuous function, then f of s is given by integral minus infinity to infinity e power minus st f of t dt. Okay, so this basically converts a function from s to, t to f. Now, what is this s looking like? This s basically will be a real variable plus, it's basically a complex number. We call it a sigma plus j omega. So we're going to look at complex plane. We're going to look at complex plane. And we're going to look at we are going to analyze. So analysis of f of t. Analysis of f of t is done in the complex plane. We call that as S plane. Okay. So what is the kind of analysis that we do? See, especially for system design engineers, especially for system designers, let's look at that. So if we look at system design perspective, system design / analysis perspective, this Laplace transform is going to give us some idea about the behavior of the system. The Laplace transform gives us an idea about the system behavior. So what does that mean? So suppose I have a system. This is a system. Suppose I have a system to which I give this input x of t, and from the system I get an output which is y of t. Now the question is, I want to see how is this system manipulating x of t to give y of t? How is this system manipulating the input x of t to give the output y of t. Right? For example, let us take a simple case. I mean, you see many students coming to your colleges. So the input to your college is basically let us assume that your college is a system. The input to the college is basically the students. Okay, the students who have just finished their class 12. What is the output from the college? What is the output from the system? The output is basically set of engineers. So what is the system that is there? The system consists of all professors and administration, which sits inside, which is the college. So the question is, how does this system, which consists of teachers and administration, all those things, manipulate the input students that we get, which is x of t, to get the output y of t, which is set of engineers? That is what we look at. Is that clear? Now, is this okay? I hope this is clear. So the relation between the input and output, the relation between input and output is what we call as transfer function. Is what we call as the transfer function or system function. So what we do, suppose we have, so now what is interesting is all these fellows, this x of t, y of t, all these fellows are in, let us say t to be the time. So they are all in time domain. Time domain is like you have t to be a continuous random variable, continuous variable. So time domain we have. So what happens is the moment you start, the moment you look at the x is equal to at t is equal to t0, you would have already crossed that. You would have gone to t1, you would have gone to t2, and so on. Therefore, the analysis of the system in a particular domain is, in time domain especially, is difficult. This is like a best example that we can look at is this. What is that? Suppose you go to suppose someone goes to a hospital for doing the surgery. Surgery is what? Surgery is basically analysis of our internal parts and rectifying it. So what people do, what does the doctor do? Does he directly, as soon as we go inside the hospital, does the doctor catch hold of it and say, look, I'm going to cut your stomach now and then do a surgery? No, he doesn't do, because in time domain, our behavior is dynamic. We are dynamic. Therefore, the function f of t typically shows a dynamic behavior in time. So now what we want is, we want to operate on a person only when he is static. We want to operate on a person only when he is static. So to get the static equivalent of a dynamic person, what do? The doctors give a anesthesia. So once the anesthesia is given, what happens? The patient gets into a static mode, and therefore now you can operate the person and then find out what are all the parts to be replaced, what are all the parts to be dislodged, or whatever, right? Therefore, your other domain, this is exactly what we call as the time domain, frequency domain stuff in case of all our signal processing and related things. So what we do is, we basically transform a dynamic thing in time domain to a static thing in frequency domain, which will help us analyze our system properly. So in this case, but before that, we need to look at some more details about this system. So what we are going to do is, we are going to look at a very specific class of systems, which we call as linear and time invariant systems. We'll call it as linear time invariant systems. In short, these are called as LTI systems. Is that okay? Now, question. What are these LTI systems? What do we mean by LTI systems? We will capture it mathematically in a few minutes from now, but then let us try to understand what we mean by. There are three terms here. There are three words here. One is linear, one is time invariant. Okay, linear, time invariant system. So we want to find out what does this mean. So what is it to say a linear system in the first place? So the first thing that we need to clarify is linear system. What is a linear system? This is exactly the equivalent of what we study in our linear algebra. What does it say? A vector space is a linear vector space if it has the zero element, and then if you take any two vectors from the set and take a linear combination of these two vectors, the resultant should be in the same. It should be the same. It should be in the. It should also be an element of the vector space. The equivalent of that is what we call here as number one. We call it as something. Linear system is something, is a system. Okay, we'll write it as system that obeys what does it obey? Law of superposition. And homogeneity. Now, what do we mean by that? This homogeneity is basically our multiplication equivalent to your multiplication by scalar, which we see there in vector space. When you take a vector and multiply it by a scalar, the resultant should be there in the same field, the same vector space. And then superposition is basically you take two vectors and the linear combination, you do a vector addition, the resultant of the vector addition should be an element of the vector space. So, but in layman terms, how do I define linear system? A linear system is something very interesting. A linear system is one which gives no output when there is no input. What do we mean by that? If you don't give any input to the system will not give you any output. Best example is our own colleges. You don't give any student as input to the college, there will be no engineers as output from the colleges. Is that clear? So that is the example of linear system. So a linear system can be classified, it is something analogous to this. Analogous to what? It is a behavior which is analogous to this. That is, it's a straight line passing through the origin. If I take this to be the input, this to be the output, then when you give zero input, the output is also zero. Is that clear? This is what we mean by linear system. Now I want to look at time invariance. Let us see what time invariance is. So I want to look at time invariant system. Time invariance slash shift invariance. What do we mean by this? Okay, so what do we mean by time invariance, or what do we mean by shift invariance? This is what we are going to look at right now. Okay. Okay. Time invariance is pretty simple. Suppose I have a system. I give this input x of t. I get this output y of t. Suppose I give the system an input x of t delayed by some amount t. Instead of giving it now, I delay it and then give the input a bit later. Then the output should also get delayed by the same amount. Is that clear? A best example is if you start late from your house, you must reach college late. It's not that you start late from the house and reach early. You start 15 minutes late from your house, you will reach 15 minutes late to the college. That is the kind of system that we are looking at. So what we do is we are going to look at linear time invariant system. These are very these are most important what do you call class of systems for which you have some interesting properties. What are the properties? Now you remember we said that if you have a system, we have something called as your transfer function. We said the relationship between input and output is what we call as system function or transfer function. So if you take a system, let me denote the system behavior by h of t, the input to the system as x of t, and the output system from the system as y of t. Is that clear? So for a linear time invariant system, for an LTI system, we get the output y of t. Again, we'll not get into the details because this is all very preliminary stuff for what we are going to build in terms of our transforms. Okay, just need to get an idea, and therefore I'm not going to do anything in detail as far as this is concerned. Then when we look at transforms, we'll probably dwell in detail. So the output y of t is related to input x of t by the convolution integral, by the convolution operation. So what do we mean by that? We have y of t is equal to integral minus infinity to infinity x of tau h of t minus tau d tau, where h of t, there is a name for that. I call it as impulse response. Of the system. What do we mean by impulse response? Suppose you have a system and to that system you give impulse as an input. What does that mean? Let us consider ourselves to be a system. Somebody comes and slaps us in our cheeks. The response that we give for that is called as an impulse response. It can die out at that moment itself, or it can get carried over for a longer period. So impulse response to a system is nothing but, let me take this system. I give impulse function del of t as input. I get output, which is h of t, where del of t is basically 1 when t is equal to 0, 0 when t is not equal to 0. This is how I define my impulse function. So the response of a system to the impulse function is basically what we call as impulse response. And therefore, the input and output of any LTI system is related through the convolution with the impulse response. This is in case of continuous. It holds good even in case of discrete. Okay. Now, this convolution is very difficult to perform because it is a pain. Because see, it is x of t, x of tau, h of t minus tau, then it goes from minus integral to minus infinity to infinity. You have to integrate all those things. So it's a pain. So what we do typically is we take the Laplace transform of this, the Laplace transform, and we will see that Laplace transform on either sides we get y of s is basically the product of h of s and x of s, where y of s is the Laplace transform of the output, x of s is the Laplace transform of the input, and h of s is the Laplace transform of our system. Therefore, now what we get, the transfer function is basically given by h of s, which is y of s by x of s. Now, this is in case of our continuous functions. Now, I want to study the behavior of this. We actually started off with the question, what is the use of transform? We want to look at that. So what we do is, I want to study the behavior of the system. This is basically my system. So this is basically my system. So I want to study how the system behaves. What do we mean by how the system behaves? There are certain systems for which you give small input, the output is going to be very huge, unbearable sound you're going to get, like your suddenly volume increase microphone or whatever. You see all that behavior, right? So I basically want to look at the system behavior through this transfer function h of s. So this y of s by x of s could be a rational function, say p of s by q of s, or let us call it as numerator polynomial in s divided by denominator polynomial in s. Is that okay? We're going to look at this. Now, what happens is, if wherever the denominator polynomial becomes 0, wherever the denominator polynomial becomes 0, what do we mean by that? H of s will become 1 by 0. What do we mean by that? The roots, exactly at the roots of this denominator polynomial, the roots of denominator polynomial. So what happens with this? Wherever you have the denominator polynomial becoming 0, what will happen to h of s? H of s will become infinity. That means the system will become unstable. It cannot give for a very minimum input, it cannot give me a completely unbounded output. So that is what we're going to look at. And when the numerator function becomes 0, that is the roots of the numerator function, what will happen? If whenever the numerator becomes 0, h of s becomes 0. Is that clear? So basically, this Laplace transform helps us analyze a system through the S domain as to whether the system is going to be stable or not. So at the roots, at the points where dr of s, the denominator polynomial of s, is equal to 0, the system becomes unstable. I mean, the stability, unstable, all those things may not be of concern to mathematical people with mathematical background and not looking into engineering applications, but it is essential that we know it. Okay, so what have we basically done? We had a continuous time function, x of t, h of t, and y of t. We converted that x of t, h of t, y of t, everything through its Laplace transform. We converted to another S domain, and then we did an analysis of the system in S domain. And from the S domain, wherever the roots of the denominator become 0, we see that the system output becomes infinity. Now that is not going to work. I don't want that. Basically, what happens? The system behaves in a bad manner. The roots of this denominator is what we call as poles of the system. Is that clear? This is what we call as poles of the system. The poles of the system is basically like this. It is like you keep a blanket on the floor. This is how it is going to be. Now what I do, I try to put a stick. I try to put a stick this way. I try to put a stick. Then what will happen? This blanket, whatever I had, is going to take the shape of that stick, whatever I have put. So from ground, it would become like this, it will become like this, and it will be like this, or it might fall. Is that clear? So this is the original blanket which is on the floor. What is happening now? If I put a stick, and these are all the points which we call as poles. Is that okay? Now what we do is, This is in the case of continuous time domain. The equivalent condition for a system to be stable is typically what we will teach as, let us say, what is that? We say the poles of the system should be on the left half of S plane. Left half of S plane. Is that clear? Now, this is with respect to the continuous function. I don't want to do this continuous function anymore because as far as system design is concerned, now everybody talks only about discrete time system, and all that we want to do is we put everything through the computer, and in computer you cannot feed a continuous time system. Therefore, what you do, continuous time signal or whatever input. So what we do, we look at discrete. So we look at the discrete case. So now what we're going to do is we're going to look at discrete case. Discrete time systems. So we're going to look at discrete time systems. That means what? The input to the system is discrete. The input is discrete. The output from the system is discrete. And the system impulse response, we'll call it as impulse response. That is also discrete. Is this clear? This is also discrete. Now, let's see what it is. So I have a system, discrete. So therefore, the moment I say discrete, I am not going to have x of t anymore. I'm going to look at x of n sequence. I'm going to have h of n. This is also discrete. And I'm going to have y of n. Now, how did we get this x of n, h of n, and y of n? We basically did sampling. We sampled x of t. We sampled x of t using with the help of using what we call as Shannon sampling theorem or Nyquist sampling rate. You have all that. Sampled x of t at a rate greater than or equal to Nyquist sampling rate. Now, what do we mean by that? You have a function x of t, you have a signal x of t. Now, what we do with this signal is, for any signal, we talk about frequency components. Yeah. I will take up your questions at the end of it. So I'm seeing some of the questions on YouTube. I'll take up all these questions later. But right now, let's first finish this off, okay? So, or equal to the Nyquist sampling rate. So what do we mean by Nyquist sampling rate? Every signal has a frequency component. There is some maximum frequency there. So what we do is we sample at a frequency which is more than, which is at least 2 times the maximum frequency. That means x of t, you have to sample. What do we mean by sampling? Sampling x of t implies sampling x of t is equal to multiplying x of t with a train of impulses, the spacing between these impulses being between impulses being 2 times, okay, I'll put it as 1 by 2 times F max. Okay, you're going to look at 1 by 2 times F max. That is the time interval between successive impulses. That means what? Suppose I have a signal like this. Sampling is like you take a sheet of paper, and in that sheet of paper, you take a comb and press the comb against the paper. I have a sheet of paper. That is a continuous sheet of paper. Now what I do is I take a comb. I take a comb and then I press this comb against the sheet. So what will I get? I'll get holes, and those holes, the magnitude of those holes from the that height basically is what we call as our. I mean, those holes are basically the samples, points at which the sampling has been done. Is that clear? That is what we are looking at. Now, this is basically our amplitude. This is basically multiplication with train of impulses. Now, here again, what happens is our y of n is related to our x of n by the convolution integral. I'll take it as x of k, h of n minus k. Again, the system is linear time invariant. This is n is equal to, k is equal to minus infinity to infinity, n is equal to minus infinity to infinity. Okay. Now there is a problem. What is the problem? I have to do infinite term summation. This is a pain. Summation infinity to this product. This is typically called a sum of products. This convolution sum is a pain. I don't want to do this. Instead of doing this, what do? We already know one technique. What is the technique? Take transform of this. Take transform of the above. So what do we get? What transform we need to take? That's a good question. So what is the transform that we need to take? If it was a continuous time function, I could actually take a Laplace transform. Now what I want to do is, it is discrete. So what I do is I go for Z transform. This is a discrete time transform. So I take Z transform. So how do I define Z transform? Z transform, if x of n is a discrete sequence, if x of n is a discrete sequence, then Z transform of x of n, Z transform of x of n, denoted as x of z, is given by x of z is equal to sigma n is equal to 0 to infinity or minus infinity to infinity. Okay, let me put it as 0 to infinity x of n z power minus n. Now, what does this expression tell us? And so what is z in the first place? We didn't know what is z. We wrote s is equal to sigma plus j omega. So what is z? So here, z is basically given by r e power j theta. So which means now we are going to look at polar coordinates. We're going to look at a polar coordinate system where z is going to be r e power j theta. Is that okay? This is what we're going to Now, that means what? So we're going to look at complex plane again. But we're going to look at circular disk. Is that clear? So we have, if you put R is equal to 1, then what happens if you put mod z? Mod z will be equal to, in this case, R. Suppose if you take the unit circle, so what do we mean by unit circle? The magnitude is going to be 1. This is mod z is equal to 1. Now, here again, I want to look at the same case. For a continuous time system, we had stability. Stability, we said the system is stable if the poles are on the left half of the S-plane. Now, what we are going to do is we are going to study an equivalent. We're going to just state an equivalent for that condition. The equivalence is this. What is that? If the poles of H of Z lie within, I should not say modulus of Z, H of Z. If the poles of H of Z lie inside the unit circle, the system is stable. So the left half of S-plane in the Laplace transform gets completely mapped onto the inside of unit circle, the interior of the unit circle. The right half of the S-plane basically gets mapped to the exterior of unit circle, and the unit circle is basically your j omega axis. Is that clear? This is what we're going to look at. Now, we will not worry about any of this, but what we are worried about is this. Y of n is equal to sigma x of k h of n minus k. K is equal to, let's say, minus infinity. I want to look at this. This convolution sum is very difficult to get. It is very difficult to get because it is infinite term summation and all those things. What we have is, to that extent, we have an easy way to look at it. What is that? If you take the transform of this variable, we already know that if you have two functions, if you want to do a convolution of the two functions, the convolution of two functions is equal to polynomial multiplication of the transforms. Is that right? So we'll write this. Convolution of two functions in one domain is equivalent to, is the same as polynomial multiplication in another domain. Let us see actually what it means. So this y of z is basically equal to x of z into h of z. So what does that mean? X of z, what is x of z? X of z is basically x of 0 plus x of 1, z power minus 1 plus etc. Let us say x of n, z power minus n. Now what is h of z? What is h of z? H of z is basically h naught or h of 0 plus h of 1, z inverse plus etc. plus h of n, z power minus n. Therefore, what is y of z? Y of z is the multiplication of these two polynomials, is equal to x of z into h of z, which is equal to polynomial multiplication. Now, my problem is, how do I do this polynomial multiplication? See, here again, if I have to multiply these huge terms of polynomial, and then how do I get my y of n from here? Y of n Now, okay, y of z, what would that be? Y of z in turn will be a polynomial in z. So to get y of n, the coefficients, pull out the coefficients of y of z. We will take an example. The coefficients of z power minus the z terms I'll put. Example. Let us take x of n to be equal to 1, 2, 3. This is the discrete sequence that we have. And h of n is basically, let's take this, 4, 5. This is what we have. Okay. Now I want to find out y of n. Y of n, I can do a simple convolution, which is nothing but I basically do this 1, 2, 3, 4, and 5. I multiply each row by each column by 4, each column by 5. So I get 4, 8, 12. Then I get 5, 10, 15. Then what I do, I add them diagonally. So y of n is basically 4, 13, 22, 15. This is what I'm going to get. But what is the other way of looking at? Let us take x of z. X of z is basically 1 plus 2z inverse plus 3z power minus 2. H of z is what? H of z is basically 4 plus 5z power minus 1. Now what we do? We multiply these two. X of z into h of z. This is equal to y of z. So what do we get? We get 1 plus 2z inverse plus 3z power minus 2 into 4 plus 5z inverse. That's what we have. The equivalent, if you see, I'm going to have 1 into 4 is 4 plus 5z inverse plus 8z inverse. I have 13z inverse. Then plus 2z inverse into 5z inverse is 10z power minus 2. Then I have a 3z power minus 2 into 4, which is 12z power minus 2. So I'm going to have 10 plus 12 z power minus 2 plus 15 z power minus 3. So what is it we get? We get 4 plus 13 z power minus 1 plus 22 z power minus 2 plus 15 z power minus 3. Now what we do? You pull out these coefficients. These are precisely the coefficients y of n. Now compare this with y of z. Compare. This is y of z. Compare with expression for y of z. Now what is that? So y of z is nothing but y of 0 plus y of 1 z power minus 1 plus etc. Y of 2 z power minus 2 plus y of 3 z power minus 3 plus y of 4 z power minus 4 and so on, plus so on. So if you do a direct term by term comparison, so what do I get? I get the following. What do we get? We basically get this. Y of 0 is equal to 4. Y of 1 is the coefficient of z inverse, so I have 13. Y of 2 is the coefficient of z power minus 2, I have 22. Y of 3 is the coefficient of z power minus 3, which I have 15. Y of 4, these terms are not there, so they all become 0. Is that clear? So they all become 0, which means now I can pull out the coefficients. Instead of doing convolution, now I do polynomial multiplication. Now, this polynomial multiplication is also not an easy job. Therefore, we need to look for computationally fast algorithms or computationally faster way of doing way of doing polynomial multiplication. Is that clear? Now we are going to look at computationally faster way of doing polynomial multiplication, for which we look at this. So let's look at this example. Look at the following. So what we are going to do is, we are going to do what we are going to do is we are going to do something interesting. We are going to take the help of interpolation polynomial interpolation to do this computation faster. What do we mean by that? What do we mean? Okay. Now let's look at this. So what do? We are going to look at something interesting. Please be a bit watchful in this, because it is easy. At the same time, it will be a bit confusing also if we don't do this properly. Is this clear? Okay, let's do this. First of all, look at this. First, let x of p be a polynomial. Okay, we'll not even look at x of p to be a polynomial. Instead, we'll do this. Let x be the sequence, let's say x naught comma x1. Okay, let x be the sequence x naught comma x1. Now what I'm going to do is I'm going to express this x sequence as a polynomial x of p, like what we did for our z transform. We took z transform, that is basically a polynomial in z with decreasing, I mean, you have negative powers. The same way is what I'm going to do now. I'm going to express x of p as x naught plus x1 p. Look at the similarity between z transform and this. The similarity between z transform and this. Then we'll finally come back to whatever it is. Okay. Pasha, again, I'll take till 3:45 if it's not a problem. And
no problem, sir. No problem.
Yeah, let h be equal to h naught comma h1 comma h2. I'll take like this. Okay, so then what will happen to h of p? H of p is nothing but h naught plus h1p plus h2 p square. This is what I'm going to do. Again, I'm going to look at the same thing, whatever I have done here. Is that clear? I'm going to do the same thing which I have done here. So now what is y of p? Let me define y of p to be equal to x of p into h of p. Again, note the similarity. Note the similarity. What is the similarity between What is the similarity? Y of z is equal to x of z into h of z. That's exactly what we have here. So what is y of p from here? Y of p is basically x naught plus x1p into h naught plus h1p plus h2p square. Is that right? So what is this? This is equal to x naught h naught plus x naught h1 plus x1 h naught into p plus x1 h1 plus x naught h2 into p square plus x1 h2 p cube. Is this okay? This is what we're getting. Now if I do this, if I had y of p to be a polynomial which is like this, y naught plus y1p plus y2p square plus y3p cube, all I need to do is compare this with this, compare this and this, compare this and this, compare this and this. Those will give my coefficients. But I still do not know how to compute these coefficients. I have to, the idea itself is to make this computation faster. So what we do is we take the help of Lagrange's interpolation for this. We take the help of Lagrange's interpolation. So what do we do with this? So we see that y of p is basically a cubic polynomial which is basically obtained as the product of a polynomial of degree 1 and a quadratic polynomial. Is that right? That is what we had here. Degree 1 polynomial and a quadratic polynomial. Polynomial of degree 1 and a quadratic polynomial. Okay. Now what we do is we compute x of p at 4 distinct p values. You choose any 4 p values which are distinct and compute x of p at 4 distinct points. Is this clear? Compute h of p at the same set of points, at the same set of 4 points, four p values as above. Let's do this. For example, let the 4 distinct points be P0, P1, P2, P3. Okay. So now what we do is I'm going to compute x of p naught. I'm going to compute h of p naught. And I'm going to compute y of p naught, which is nothing but x of p naught, h of p naught. Is that right? I can do this. Similarly, I do the other ones. X of p1, h of p1, y of p1, which is xp1, h of p1. I go there, x of p2, x of p3. I compute this, h of p2, h of p3, y of p3, p2, y of p3. So I'm going to do a pointwise multiplication of the two polynomials. Is this okay? I'm going to do, I have to do a pointwise multiplication of these four polynomials. So I have got those values. What are those values? I have y of p0, which I'll then y of p1, y of p2, and y of p3. These are the 4 points I have. Is that clear? Now, look at what I'm going to do. I'm going to use Lagrange's interpolation. I'm going to use Lagrange's interpolation to get the coefficients. And get the coefficients, which is y0, y1, y2, y3, which is what we had put here. These coefficients I'm going to get now from Lagrange's interpolation. How do I do Lagrange's interpolation? I know that given a function whose values, given a function value at n plus 1 distinct points, what does the what is that? What does Lagrange's interpolation say? If it says given a function value, given function values, a particular function whose values at n plus 1 distinct points, let us say, then there is exactly one polynomial of degree n that passes through all the n plus 1 points, and that is given by so we will take up this directly. We'll take up this example itself. We have y of p is nothing but, what is that polynomial? Y of p is nothing but y of p0 into p minus p1 into p minus p2 into p minus p3. We'll take with a reference to this specific example, the above example. Okay, that's what we're trying to do. Divided by p0 minus p1 into p0 minus p2 into p0 minus p3 plus y of p1. Do the same thing, p minus p0 into P minus P2 into P minus P3 divided by P naught. Oh, no, okay. P1 minus P naught into P1 minus P2 into P1 minus P3 plus y of P2 into whatever terms that we have plus y of P3 into that term by this. So we end up getting our coefficients very easily from here. Now, why do we want to use this? The advantage of using this is basically there are two things. Whenever I try to do convolution, the number of multiplications and number of additions will be a bit too much. The number of multiplications will be too much. Whereas in this case, what we have is the number of multiplications to be reduced. If you take two sequences of length, let us say 5 and length 10, then the number of multiplication will be, how much we'll have? Okay, convolution, if you take, it's going to be LM. So you're going to have 50 times 50 multiplications you need to do. Whereas if you're going to do this, I'm just going to have 10 plus 5, 15, approximately 15 multiplications, which basically gives me reduction in computation. Is that clear? Therefore, the order of computation, the computational complexity in this case, the computational complexity reduces from order of ln to order of L plus n minus 1, where L and n are the lengths of the two sequences. Is that okay? Is this okay? Now what we do is, this is a bit dry, but still please understand that whenever you want to do discrete time convolution, all you need to do is it is equivalent to polynomial multiplication. And polynomial multiplication, you do pointwise polynomial multiplication and then use this interpolation to get the coefficients. This is much faster than a direct convolution. Is that okay? In fact, you can even do this. What is it that we can do? We can even do this. We can even follow matrix approach for this. Now, what is the approach? Here I have, we had y0, y1, y2, y3. These are the 4 values that I need to find out, right? This is what I need to find out. I want to get, I want to get in terms of, how do I go about doing this in terms of matrix? I can do this matrix business. 1, P0, P0 power 1, P0 square, P0 cube, 1, P1, P1 square, P1 cube, 1, P2, P2 square, P2 cube, 1, P3 square, P3 cube. This is what I have. I want to find out these coefficients. I have this. So basically, what am I trying to do? I am going to look at this. I'm going to look at, I will come to this. What should go there? We will check it there. Okay. So what is it that I want? I want to look at this. So I have y0 of P is nothing but equal to, I'll say y0 of P0. Y0 of P0 is what? Y0 of P0 is y0 of p0 this is basically a polynomial which I don't know. Let's look at this value is known. This is known. What is this equal to? X of p0 into h of p0. So we have to look at the inverse of this into this value. What are these values? These values are inverse into x of p0 into h of p0, x of p1 into h of p1, x of p2 into h of p2, x of p3 into h of p3. If you take the inverse of this matrix and multiply it with the function values that we get, we basically get the coefficients of our polynomial that we want. And that in turn becomes the resultant sequence. Okay, this is with respect to doing convolution, discrete convolution through a transform technique, which typically transforms, we treat them as polynomials and we start working in polynomial. All those concepts which are applicable to polynomial theory will be applicable here, majority of them. Therefore, what you use the properties of polynomials and try to evaluate this. The next important thing that we're going to do is fast Fourier transform algorithm. Okay, the next important, that's the most important stuff which is used. So we're going to look at fast Fourier transform algorithm. I will just give a intuition about this. I may not be able to cover it completely. I'll just do an intuition of fast Fourier transform. This is an algorithm which most of the electronics and communication engineers and electrical signal engineers, they will use. This is basically to compute the discrete Fourier transform. Okay, so this is basically to compute the discrete Fourier transform. See, Fourier transform, we already know it exists both for continuous and discrete sequence. Continuous sequence, you put that, okay, for if x of t is continuous, if x of t, then we have x of omega, which is nothing but integral minus infinity to infinity, x of t e power minus j omega t dt. This is what we have. If it is x of n, then we have two things. One is sigma x of n, e power minus j, I'll put a different notation, j omega n, where n is equal to, let's say, minus infinity to infinity or 0 to infinity. This n is basically discrete index, whereas this omega is basically a continuous one. You remember, we looked at the Z transform of x of n. Z transform of x of n was basically this, sigma x of n z power minus n. Now, what I do is, I am going to evaluate, I will say x of e power j omega. This is equal to sigma x of n e power minus j omega n, which means what am I doing? This is basically obtained by evaluating Z transform on the unit circle. On the unit circle. Then we get this, and this e power, whatever that we see here, this is called discrete time. It is only discrete in time, and the Fourier transform is basically continuous. So this is discrete time Fourier transform, which we call as DTFT. Now the problem is x of n is discrete, x of omega is continuous. So this is some kind of thing which I don't want, because x of n is discrete means finite I might get the sequence, a finite length sequence. If I put, I must get a finite length sequence on the output. But x of omega being continuous, I'm going to have infinite number of values. Therefore, what I do, I want to sample this continuous fellow. This DTFT, this is continuous. So I want to get the discrete equivalent. I want to get discretize this. So how do I discretize this? Whatever sampling that I do the same thing here. Therefore, what happens? I get if x of n is discrete, if x of n, then we define x of k, which is the discrete Fourier transform, which is given by sigma n is equal to say some 0 to n minus 1, assuming that I have only n minus 1 n samples of x of n. I have x of n, we have e raised to minus j 2 pi k by n into n, and k is equal to 0 to n minus 1. This is very simple way of looking at discrete Fourier transform. I had continuous Fourier transform for a continuous time signal. If I discretize the time domain signal, then I get a continuous time Fourier transform, which I get a discrete time Fourier transform. Now I want to sample the discrete time Fourier transform to get to get the discrete Fourier transform. So this is basically my DFT. Now what is interesting is, suppose I want to compute this x of k. Assume n is equal to 8. That means I'm going to compute an 8-point discrete Fourier transform, 8-point DFT. Now, what do we mean by 8-point DFT? I have x of n, where n varies from 0 to 7. That means I'm going to get x of 0, x of 1, and so on, x of 7. This is what I'm going to get. Is that clear? Therefore, DFT also will be similar to this. I will have x of k, where k varies from 0 to 7. Therefore, I'm going to get capital X of 0, capital X of 1, and goes on till x of 7. Is that clear? Now, I want to compute this. How do I compute this? That's where the problem comes. So let me put it in a matrix form. I can put this as x of 0, x of 1, till x of 7. This is my DFT vector, column vector. This is equal to, since n and k are going to be the same number, so I'm going to get an n cross n matrix and multiply it with x of 0, the small x of 0. This is the time domain. So I go on till x of 7. This is x of k. This is x of n. So I'm going to have an n cross n matrix. This matrix is a complex matrix because I'm going to have all kind of e power minus j and all those stuff. Okay, now there is a problem with this. What is the problem? If I have to compute x of 0, I have to multiply this number with this number, this number with this number, this number with this number, and so on, the last number with last number, which means I have 8 complex numbers here. I have 8 numbers here. This could also be complex. So for getting one x of 0, I am going to do something like 8 square multiplication. Is that clear? So what we have is, the problem is this. If we want to do computations, if you want to compute so how many multiplications I'm going to do? I'm going to do first multiplication, second multiplication, third multiplication, and so on, 8 multiplications. So one row into this column is going to have 8 multiplications. Therefore, 8 rows into this one column will have 8 square multiplication, which is n square multiplication. If you want to compute the DFT of an n-point sequence, we will look at only of an n-point sequence. We will very specifically look at one type of n. What is that? Where n is equal to, say, some power of 2. 2 power r will take. For no other thing we are going to look at. We are going to make it very, very, very specific and say n is equal to 2 power r. N-point sequence, we need n square complex multiplication. And every row will have n minus 1 additions. So if you have 8 numbers to be multiplied with 8 numbers, dot product you want to find out, I'm going to do 7 additions. And there are 8 rows. Therefore, I'm going to have n into n minus 1 complex additions. Is that clear? Now, this n square complex multiplication is a pain because for every multiplication of 2 complex numbers, I'm going to do 4 real number multiplication. I don't want that. See, whatever it is, we want to make our life very easy. We want to live in the lazy world where things are done faster, efficient, and there is no slow thing that is involved. And especially in terms of computations, we don't want to do any large number of computations. We want to avoid as much computations as possible. Yeah, that is why if you see most of the bus tickets and all, if you see what have they done, they've all made it integer numbers. Bus ticket is 6 rupees. You pay 10, you get 4. Nowhere the bus ticket says it is 6.5 rupees, 6 rupees and 75 paise. Nobody says, because that computation is very difficult to get. So to make our life easier, what we do is we look at reducing the number of multiplications in this case, especially because it is a complex multiplication. Is that okay? Now, how do we do that? Now, before we get into this, let us take up a simple example. Let's take this example. Consider f of x is equal to x squared. Okay. Now I tell you, compute f of x at 2 distinct points. Now we say compute this at 2 distinct points. What do we do? Oh, the most laziest fellow will do f of 0 is equal to 0, f of 1 is equal to 1. I would still have to do this computation. A most intelligent fellow, what he will do, he'll say, look, f of plus or minus 1 is equal to 1. Why he will do this? Because he knows f of x equal to x square is an even function. So f of x equal to x square is an even function. Therefore, f of plus or minus x, f of plus or minus x is equal to x square. Now, what do we mean by f of plus or minus x equal to x square? If I tell you do computation at 2 distinct points, I am actually cheating the system now by doing only one computation and then say, look, I have done 2 computations, because I know plus or minus k is equal to f of plus or minus k is equal to k square. So if I have a function which is even, I actually, this implies for even functions, the computations reduce by 50%. Straight away, the computations reduce by 50%. So what do we mean by that? If we want to do n points, if we want to compute an even function, or if we want to evaluate an even function at n points, do only n by 2 computations. Why? Because we know, f of minus x is equal to f of x, which implies f of plus or minus x is equal to f of x. Is this clear? Therefore, I straight away get a 50% savings in computation. Now, I want to look at something more. What is that? Now, let us consider this. Consider this, the following polynomial. the following polynomial. That is, let me call that as A of P. A of P is A naught plus A1P square, A1P plus A2P square plus etc. plus A7P power 7. I'm going to look at this polynomial. The question is, compute A of P at 8 distinct points. Is that clear? Now, see, just a few lines before we saw, if the function is even, if the power of x is even, I can cheat the system saying f of plus minus x equal to f of x, or f of plus or minus x is the same. But now what we see, this bloody function that we see here, this is not an even function. This is an odd function. This has power 7. I have to exploit that property of even function. If I do that, I'll get 50% savings. But what do I see here? I see something different here. This is power 7. Now that is going to give me a trouble. But let's see, how do we overcome this trouble? So what we do is this. Let us see how to compute this directly. So what do I do? If I have to compute this directly, this A of P, direct computation. Let us check that. Direct computation. Let us see what happens, okay? Of A of P. What does this direct computation of A of P do? Oh, this is basically, I take A naught. I'll do a graph theoretic, signal flow graph theoretic way of doing it. I'll just show you that. And then let's see what happens. A naught gets, it has to be added with A1 into P. Then what happens? This has to be added with, one minute, I'll redraw this. So I have A naught. Then what happens? This A naught has to be added with A1 into P. Then what I should do, I have to add this with A2 into P square. I have to add this. Then I have to add this with, I should be doing this. Oh, now what I do, I add these two fellows. This is A2 P square. Then what I do, I add these two fellows. A3 P cube. Now you'll ask me a question. Why should you add only two things at a time? This is one number that you add. This is another number that you add. Why can't you add too many things together? I will give an explanation for that. Okay. Then this result has to be added with A4 P power 4. This result has to be added with A5 P power 5. This result has to be added with A6 P power 6. This result has to be added with A7 P power 7 to get my A of P. Where I keep supplying this points P. Okay, where I keep supplying these points P, this is going to be extremely difficult because 8 points I have to add. Now what happens if I put to a computer microprocessor that you say, which goes and sits inside the computer, which is essentially the one which is going to do the computation, it can take only 2 inputs at a time. And that's exactly why I have marked 2 inputs here. So what happens? First of all, I have to do A0. Then I should multiply it with A1 with P and then add these two. Once I do this, till I finish getting this A0 plus A1P, this sum, which I'll call it as S1, I cannot do anything. Then I get A2 plus P, A2P square. I add these two, I get S2. Then I have to wait for this S2 to come. Then I will add this. It becomes S3 and so on. Therefore, there is a lot of delay involved to get my A of P. There is a delay involved, lot of delay. I don't want to do this. This is painful. And you see, suppose if somebody, some crazy guy like me says, I evaluate this A of P, compute A of P. At P is equal to 7,927. Oh, that is a deadly number. Because I can do A0 plus A1P, T square is also fine. P power 7, if I do computer, the calculator will say, mind your business. The calculator will say, what are you trying to tell me? 7,927 power 7, you think I don't have better job? It will say that. So, now there is a problem because this P power 7 and all I have to compute, it is going to be extremely difficult. So what I do, I want to exploit the property of my even function. Let us see how to do this. Let us try to rewrite this A of P as, this is what we had, A0 plus A1P plus A2P square plus A3P power 4 or A3PQ plus A4P power 4 plus A5P power 5 plus A6P power 6 plus A7P power 7. This is what we need to compute now. What we'll do is we'll slightly do a small jugaad. Again, we are trying to cheat the system. Let us see what to do. Let me do this A0 plus A2P square plus A4P power 4 plus A6P power 6 plus P into A5, okay, P into A1 plus A3P square plus A5P power 4 plus A7P power 6. I have done this now. Is that clear? I have done some jugaad where I collected all the even index term together and where I collected all the odd index term together. Pulling a P out, I see something interesting here. Okay. Now what I do, cool. I have collected all the even powers and I've collected odd powers. Suppose if I again tell you evaluate at P is equal to 7927, it is still a problem because P power 7 and P power 6, it is not a great, what do you call? There's no difference. If I can calculate P power 6, I can actually calculate P power 7. So it doesn't make any difference. So what I do, I still go for one more iteration. What iteration that I do? I do this. I do this. What is that? A0 plus A4P power 4 plus P square into A2 plus A6P power 4 plus P into, again I'll take P square out, P into, sorry, A1 plus A5P power 4. Oh, I'll just share this screen a minute.
Okay, sir.
Yeah, I'm just restarting the screen. Okay. Yeah. A5 P power 4 plus P square into A3 plus A7 P power 4. Now, do we see any difference here? Oh, of course, we do see a difference. What is the difference that we're seeing here? We see that all these fellows are even functions. P power 4, P power 4, P power 4, P power 4. But now I can do this cheating business.
Sir,
right? Yeah.
Screen is not shared.
It is shared. Just now it got, again it got, just a minute. It says you need to reboot the system. I think the screen is available now.
Yes, sir. Yes, sir.
Yeah. I don't know what is. I'll just check. So this is what I have. All these are even powers. Therefore, I oh no, there's nothing wrong. Can you just give me a minute? I'll restart the system. It says I have to restart the system. I'll just quickly restart. Pasha?
Yes, sir. Yes, sir. Yes, sir.
Yeah, just give me a minute. I'll just restart my system. Okay.
Yes, dear participants, speaker will be back in a few seconds. Till then, most of you are asking for feedback links and other things. We have already created WhatsApp group and we have clearly mentioned that we are not going to send any mail regarding it. So those who have not joined the WhatsApp group are hereby requested to send a mail to azpa4rit@gmail.com. I'll send a message. You join the WhatsApp group and then you will start receiving the feedback links. Thank you. Welcome back, sir.
Thank you. Thank you. Sorry for the stuff. I don't know. Some
it's
random
okay.
stuff happened. I had to restart.
Okay.
Okay. Yeah. We're going to wind up in another 5 minutes, so it'll be done.
Okay, sir.
Okay. So now what we see all these functions under, which are the green lines. Oh, just a minute. Just 1 minute. So all the 4 underlined terms are even functions. Therefore, what we do, we exploit the property of, we exploit the property of even functions. Now, what do we mean by that? Now, let us see what happens. I do this. I take A0, then I take A4 P power 4. Now, what do? I add these two fellows and keep it like this. Then what I do? I take A2 and then I take A6 P power 4. I add these two and keep. Then what I do? I do the same business here. I have A1 and then I have A5 P power 4. I do this. Then I have A3. Then I have A7 P power 4. I add these two fellows and I keep. Then what I do? I have to add these two fellows. But with what? This has to be scaled by P square. And similarly, I have to add these two fellows. And the lower term has to be scaled by P square. That is what we see here, right? We see P square into A3 plus A7 P power 4. That's what we see here. And P square into A2 plus A6 P power 4. That's what we see here. Then what we do? We do this. We take these two and then we do this, multiply this with P. So this I'm going to get A of P. Now, what is the advantage of doing this? What is advantage of doing this? Oh, this is easy. The advantage is the following. What is the advantage? You look at this, and look at this one. In this case, at every time your power of P keeps increasing. So you have to do that much computations, and then you have to do that much computation every time. Whereas in this case, what happens? In all the first stage, let me call this as the first stage. In all the, okay, let me call this as the first stage. In all the first stage, what we see is each of the second arm, this one, this one, this one, and this one, they all get multiplied by the same weight, P power 4. In the second stage, what happens? This second arm and this second arm gets multiplied by P square, and in this case, it gets multiplied by P. So what happens? All of them are done, and all of these everywhere. This is an even function. This is even function. The only place where you need to do is take this P. That will be the only computation which we'll do. So what we have at every stage, my computation gets reduced to n by 2. And how many stages I have? There were totally 8 points. I have stage 1. This is stage 1, stage 2, and I have stage 3. How is 8 related to 3? We are going to look at log n base 2. If you look at log n base 2, log 8 base 2, I'm going to get 3. So that is why we said we are going to look at the sequence to be of length 2 power r. So what we get, instead of n square computations, we now have n by 2 log n base 2 computations. This will work only if n is equal to 2 power r. Works only if n is equal to 2 power r. Okay, it does not work in any other way. There is one problem here. What is the problem? The numbers appear in natural order: A0, A1, A2, A3, A4, A5, A6, A7. Whereas here, what happens? A0, A4, A2, A6, A1, A5, A3, A7. You get random ordering. So how do I get this? How do I get? Suppose if I store all these A0, A1, A2, etc. in memory, if I put A0, A1, A2, A3 in sequence, then I can access successive locations. It is like your roll numbers that you write for the students. You write it in roll number way, it is easy to access the students' attendance. Suppose if somebody says, no, you pass on sheet and ask the students to write the names, then the names will be in jumbled order. And then it becomes a work on us to rejumble them and then get their proper attendance. So that is going to be a pain. So how do we cater to this? We see that in the natural order, I have this 0, 0, 0, 0, 0, 1 in binary. 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. This is it what I have in binary. Now in our new technique, what we have 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0. Then we have 0, 0, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1. This is what we have. What we see is, suppose if you put a mirror here, and show these numbers, this is how the numbers will look. It will look a reflection of these numbers on the left-hand side. The reflection of the numbers on the left-hand side in a mirror is the right-hand side numbers. So how do I generate this? Oh, that is easy. What we do here is we add 1 to the least significant bit every time to get the successive number. Here what I do is I add the most significant bit. I add 1 to the most significant bit. So I get 1, 0, 0. I add 1 here, I get 0, 1, 0. I add 1 here, I get 1, 1, 0. I add a 1 here, I get 0, 0, 1. I add a 1 here, I get 1, 0, 1. I add a 1 here, I get 0, 1, 1. I add a 1 here, I get 1, 1, 1. Okay, this is what we call this bit reversed way of doing our fast Fourier transform. Now, let us transform this entire, let us take up this entire green thing, whatever we have had. Let us see how it is applied to our FFT. Our FFT, basically, we started with this kind of a matrix. This is the thing that we had for DFT. Now, what you do is assume this entire thing is a polynomial. You will have, if you take n is equal to 8, you get a 7th degree polynomial. And 7th degree polynomial is what? X of k is equal to 0. So you put k is equal to 0 here. It will be in terms of n, a polynomial in terms of n you get. Is that clear? So you get x of n p power 0, x of n p power 1, x of 2 p power 2, x of 3 p power 3, where p is equal to e power minus j 2 pi k by this n. Then what we'll get? We will basically get this to be p power n. So it also becomes a polynomial. Now, whatever we have done with this polynomial is what we are going to do there. And that will lead to a reduction in computational complexity from n squared to n by 2 log n. Is that clear? So what we do is, I mean, whenever we look at transforms, especially the kind of discrete transforms that we are looking at, it is always easier to look at it in terms of a polynomial perspective, especially when you want to look at computations and all. It is always easy to look at polynomial perspective. And that polynomial perspective is going to help us apply all those tools and techniques which we have for polynomial theory. And that makes all these things very easy. Okay. So with that, I conclude. I could have done a bit more, but I think we have crossed the time by another half an hour. So on another occasion, let us take this fast Fourier transform probably in detail, and let's try to do it.
Okay. So thank you, sir.
Thank you,
please
Pasha.
unshare the screen, sir, to take
Just
up
a
a few
minute.
questions.
Yeah, definitely.
With your permission.
Sure. Done. Yeah, Pasha.
Yes, I'm just going through it. So there is a question from Aishwarya G. Why should the poles of the system be towards the left half of the S-plane?
That's very good. See, if the poles are on the left half of the plane, see, when we say the stability is an issue, if the poles are on the, if you look at e power minus st, it basically becomes e power minus of sigma plus j omega t. It becomes e power minus sigma t minus into e power minus j omega t. That is what it becomes. Now, if you have poles on the left hand side, it would naturally lead to a converging thing. You'll have a convergence, and therefore the e power minus term, that term will not help you explode. Therefore, there is a decay and it will converge. Therefore, the poles have to be on the left half of the S plane.
Okay. So second question from Shashikala.
About
the Laplace transform used in electrical circuits.
It is the same. It is the same. Laplace transform is used in electrical circuits. You take differential equation and try to solve the most famous problem. If you can solve using, you can use Laplace transform to solve differential equation, where you will convert it from differential equation to algebraic equation and then do it. So you can do that also.
Okay.
Yeah.
So one more thing, Ibabu Kiran has asked this. Maybe applicability to Ramanujan sum, sir.
Actually, this Z transform somewhere, and you have even discrete Fourier transform. You have it for Ramanujan sums. I'm not quite into it. Probably I can point to some literature for that which you can look at. You can look at Ramanujan sum and Fourier transform itself. You have a couple of papers on that.
Yes, thanks a lot, sir, for
Thank you, Pasha,
for the informative talk on discrete transforms.
Thanks a lot.
Okay, so dear participants, with this we'll end today's session. We shall meet tomorrow at 11 a.m. Thanks a lot for your cooperation.
Thank you. Thanks to all the participants. Thanks for staying till the end and then listening to the lecture. Thanks a lot. And thanks to MS Ramaiah and team for this wonderful.